We are in our last 2 days of lecture.
Are we going to get to this?
I don't know. We're going to find out.
This is the exciting part.
Do you think there's a chance?
I do think there's a chance. Worksheet for anybody from yesterday?
It's the same one.
Same one.
That's mine at home, but I've got it.
Okay. I've got plenty if you need another. So there's a chance we get through everything. I definitely want to get through the heavy stuff. What I'm doing for the first time this semester that I haven't done with my classes before is I'm giving these reaction diagrams filled out. What it used to be is that this would be a blank sheet and that we would spend the time in class to go through it. You guys saw what I did this year, which was give it to you filled out, but then I had you take notes on each reaction. We're going to do that again. First, I want to wrap up about the synthesis of alkynes, which we said was an elimination reaction. Why is it obvious that it's an elimination reaction to go from a dihalide to an alkyne?
Because you added another pipeline.
Yeah, that's tricky language, though, to use added.
Or I guess.
We've created a pi bond. We've created unsaturation. And to say we've created unsaturation, maybe it makes more sense to just say we've unsaturated the molecule.
Well, we've eliminated saturation.
We've eliminated saturation. We've eliminated what saturated? Well, as it turns out, we're actually going to name elimination one of two things. Either the reaction kinetics depends on the concentration of two chemicals at the same time, or the reaction kinetic depends on the reaction of one chemical. When we look at a reaction, like this, we've got two reactants. If the rate of the reaction, you guys know what rate is?
It's like reaction over time.
Over time, change over time. That's what rate is. You know, you hear those police reports, they were moving at a high rate of speed. That's the change, actually a high rate of speed.
That was an interesting example.
Speed already sounds like rate, yeah. And that's what bugs me when I hear it. But they'll say rate of speed, they're saying you're moving fast. Rate of a reaction, how much is changing over time? How quickly does it change over time? So the rate is equal, can we call these A and B? If the rate is equal to the concentration of A and B, we say that the rate is second order. If I double the concentration of A, I double the rate of the reaction. If I double the concentration of B, I double the rate of the reaction. If I double the concentration of A and B, I quadruple the rate of reaction. This is a second order reaction. That's what we call it, second order, because it depends on two things. There are two impacts to it. If, and I should say that these are ifs we're starting with. If the rate of the reaction is equal to A, or the rate of the reaction is equal to the concentration of B, but not equal to the concentration of both. Or another way of saying this, if actually I think I'm missing K. We're not doing math though, so just forgive my sloppiness. We're not going to do math, I'm just giving the background for the names. If the rate is dependent only on the concentration of one of the reactants, then we say the reaction is first order. How do you know if the reaction rate depends on both of them or just one of them? This comes from the rate determining step. That is the highest energy in the reaction coordinate diagram. So something that has only one step, well, that's conveniently the rate determining step, and any molecules involved in that step are dependent in the rate. But if we have a reaction coordinate diagram that has two different steps with different energies, it's whichever one is hardest to do. Whichever one takes the most energy, that's called the rate determining step. What this means is you can look at a mechanism, and if there's a step where only one reagent is involved, that's a first order step. That step only requires one reagent. If you look at a mechanism and two chemicals are needed at one step, that's a second order step because both chemicals are needed for the step to proceed. When we did the elimination, were there any steps that depended on just one structure? That just one compound undergoes a change? Both of our steps required the alkyl halide and the base. You guys remember the mechanism we showed yesterday? The base takes a hydrogen, the CH bond forms a pi bond, and the halogen leaves. Both reagents were necessary. So we call this type of elimination E1. No, I'm sorry. Because both were necessary. E2. That's just the silliest little mistake. I can't. Second order, because Elvira was saying she wished someone would make a little clip of all my funny little, mark the time down and.
A compilation, if you will.
Yeah. And that's how it'll start.
You should create a TikTok where you post. Okay.
I can't even grade my labs, okay? I'm not going to go be a content creator. The elimination reactions that we've already learned about are E2. That's what I want you to get. We're going to look at some elimination reactions that are E1, but these are E2 elimination. That is second order elimination.
So both reagents are involved in the elimination for us.
Both reagents are involved in the rate determining step.
Oh, okay.
It requires both molecules to react. Like, I want you to imagine this. I have a cap and I have a marker with a cap. And I'm going to swap these, substitution. If I first remove the cap that's already there, did that depend on this molecule at all?
No.
That's a first order step. Then those two molecules can come together. That's a second order step because it depended on both of them coming together to react.
So you're not characterizing the entire.
We're not characterizing the entire reaction, just the rate determining. And what's the hardest thing to do? Oftentimes, the hardest thing to do is form a carbocation, break something apart. And we haven't formed any carbocations here.
Is there only one rate determining step for reaction?
Yes. Yes, one step that requires the most energy, everything else.
Usually breaking into a carbocation.
We're going to look also at substitution being first order or second order. So we're going to have first order and second order elimination, E1 and E2. We're going to have first order and second order substitution, SN1, SN2. We're not going to use this for addition reactions. We don't describe addition reactions as A1 or A2, which I don't know why, because they chose not to, but you have a lingering question?
No.
Okay. Then, oh, Saray, thank you.
For synthesis of alkynes, do we only use halides?
Alkyl halides. Yeah, I've not seen the synthesis of an alkyne without alkyl halides.
So if we were, let's say, starting with something that doesn't have
An alkyl halide.
we would add it and then use that.
Exactly. You'd have to create an alkyl halide in order to create an alkyne. And that's a synthetic route. Start with something that can't make an alkyne, make it able to make an alkyne, and then make the alkyne. And we're going to show those types of synthetic routes. All right, The next thing that we can do, or the first thing that we can do with alkynes, alkylation of alkynes. What does alkylation mean? It means I'm going to give my alkyne an alkyl group. What's an alkyl group? Sorry? Yeah, just like a carbon group. And it is going to be sp3 hybridized carbons. But alkylation just means put a carbon chain onto here. This is a substitution reaction where the alkyne acts as a nucleophile. In order to make the alkyne a nucleophile, it has to be deprotonated. So this reaction, it only works with acetylene and terminal alkynes. An internal alkyne can't become a nucleophile. An internal alkyne already has its bonds taken care of. So the way that we run alkylation is we first deprotonate. We need a strong base. And it's that deprotonated alkyne. This is sometimes called the acetylide ion. It's related to acetylene, but the IDE is trying to tell you it's negatively charged. And this is our nucleophile substitution. Then we introduce an alkyl halide. And these alkyl halides should predominantly be primary alkyl halides. So think of things like a methyl halide or ethyl halide, isobutyl halide. Sorry, my X's got really weird. Even phenyl halide, sorry, benzyl halide. We're often looking for these primary carbons, which will serve as the electrophiles. Nucleophiles donate electrons, negative magnets. Electrophiles accept electrons, positive magnets. If we show a mechanism here, it's that lone pair on the alkyne that attacks the carbon of the alkyl halide, kicks off the leaving group, and leaves us with a new carbon-carbon bond. Mm-hmm.
So you're saying the carbon directly connected to the halide,
Mm-hmm.
that becomes the electrophile?
Yes, the electrophilic carbon is the carbon directly bonded to the halide. The electrophilic carbon is the one with the leaving group. So if these were my electrophiles, actually, let's make these more specific. If I had methyl iodide, if I had ethyl bromide, if I had isopropyl chloride, if I had phenyl tosylate, OTS, I want you guys to recognize as a pseudo halogen, a pseudo halide. Anything that halides can do, OTS can do just as well. And I know earlier you were asking about just halides with elimination. We don't usually use tosylates there, but maybe in theory you could. How many molecules interact in that one step? Two molecules. So this is nucleophilic substitution. The carbon is being substituted by a nucleophile. And this nucleophilic substitution is second order. because it depends on both the nucleophile being present and the electrophile being present. They both have to be present in the same step. So we call this type of reaction SN2. Remember, E2 was second order elimination. SN2 is second order nucleophilic substitution. That's what the N stands for, nucleophilic. Yeah, it's often written as a subscript N. I sometimes, when I am typing it on a computer, I'll just use a lowercase n instead of actually making it a subscript. You'll see all types. But it's meant to clarify substitution. It's not an electrophilic substitution, it's a nucleophilic substitution. You'll never actually see SE1 or SE2. So why they didn't just call it S1 and S2, I don't know. They didn't consult me. There's a lot of things about the way that they present this material, and they being the broad scientific organic chemistry community. There's a lot of things that I would not have recommended. This is a two-step process. First, the alkyne needs to be deprotonated. Then it can be a nucleophile. But there's no reason we can't show those two steps at once. So we can write these over the arrow as I have an alkyne. I'm going to first deprotonate it and then introduce an electrophile. In fact, if my alkyne is acetylene, acetylene can be alkylated twice, one at both positions. First, I deprotonate it, I do alkylation. Then I deprotonate it, and I do alkylation. And now I have a final product that has taken acetylene and converted it into a terminal alkyne. Excuse me, an internal alkyne. Alkylation of the alkyne. It's your first introduction to substitution. Lastly, we can actually show all of this before the alkyne. This is the same base that we use to make an alkyne. So if an alkyne is being formed, if a terminal alkyne is being formed, there's the potential for it to be deprotonated as it's formed. This would look like taking a dihalide and exposing it to an excess amount, at least 3 equivalences. First equivalence does the first E2. Second equivalence does the second E2. And the third equivalence deprotonates the alkyne. You can show it forming that deprotonation, that deprotonated alkyne, the acetylide ion, directly from the dihalide. First, one equivalence does one elimination. Then the second equivalence does the other elimination. Then the third equivalence deprotonates. You guys okay with this?
Because there's an unlimited, or not an
An excess amount of that base. Yep. Now, you might see this on active, where you want to form the alkyne, but you don't want to do alkylation, but it's a terminal alkyne and it might be deprotonated. So you'll actually see first an excess of a strong base, followed by an acid workup. When we say acid workup, what we really mean is take whatever that deprotonated form is, give it a proton back. This might feel like 3 steps forward and then 1 step back. Why didn't I just move 2 steps forward? And the reality is because with these chemical reactions, sometimes you can't stop that third thing from happening. So once it's happened, just lean into it and then work it back. So 2 different ways that you might see synthesis of an alkyne. We might just show it as form the alkyne. Don't worry about how the excess might deprotonate it. We might show it as form the alkyne with an excess of base. Make sure you work it back into the alkyne. Okay, you got a question?
Yeah, I was just going to say, so with this being, this example that you showed, with it being like a second order step, right? Because it's dependent on the strong base being there.
Sure.
If it's an excess, is that reaction going as fast as it can?
Yeah. Yep. And actually, that is why we use excess of reagents a lot of times. It will speed up the rate of the reaction, pushes the Chatelier's principle too, towards to favor the products. Good. Also, we can heat it. Usually heating a reaction will make it go faster. All right, that's all that I have for you on elimination and substitution for right now, which means that the other things I want you guys to see are just these 5 alkyne addition reactions. I'm going to give you guys some notes. And we're going to move over to the back side. I'm actually going to start on the left, and I'm going to go counterclockwise. We can do HX addition. We can do HX addition to our alkynes, but because there's 2 equivalences of pi bonds, we can actually control how many equivalences of addition we do. 1 equivalence of HX gives a vinylic halide. You guys remember what vinylic means? What is it, Evelyn? Not adjacent to it. Adjacent would be allylic. That sounds like anti. Across? Attached to the alkene, bonded to the alkene. PVC, polyvinyl chloride, that vinylic attachment. And it's Markovnikov, because there's a carbocation intermediate, Markovnikov. Would you guys believe me that you could easily do this mechanism? You've seen this. Pi bond acts as the base. Halide is kicked off. The only difference now is that our carbocation looks kind of weird. Our carbocation is not your normal. It's not the carbocations we saw from our alkene addition reactions. That is an sp carbocation. You see how I kept it linear? That's its geometry. It's a linear geometry, 2-electron domain carbocation. But anything that we can do once, we can do twice. So we can either have 2 equivalences of HX, or we can have an excess of HX. This will always form a geminal dihalide. And it's because after the first reaction, the second reaction proceeds in exactly the same way. Oops. Oh, I'm sorry. I'm showing X, but you guys know how often I want you to show X? Yeah, never. Because I want you to use whatever is specifically provided. So use HCl if it's shown, use HBr if it's shown, use HI if it's shown. What did I show? HX, okay. So do as I say and not as I do. Do you see how that is not different at all from our alkene addition mechanism? The only difference is that there was a halogen attached this time. And if you're confused about the conformation, I did go from zig-zig to zigzag. I did change the conformation of my product from that intermediate. Okay, HX addition. Basically the same as alkenes, but we can do two equivalences. Moving on, as we go clockwise, we've got oxymercuration. When we did this with alkenes, we had oxymercuration reduction. No more reducing agent now. We're working with mercury sulfate and sulfuric acid. And I want to show you guys something interesting that this reaction does. I'm not going to ask you to know the mechanism for it. I'm not going to ask you to show the arrow pushing. But this reaction is a Markovnikov hydration. It adds H and OH. It adds H to the less substituted carbon. It adds OH to the most substituted carbon. It's still Markovnikov, just like it was with alkenes. Is that your product? It's not. This is actually a structural isomer of your product. It's referred to as a tautomer. And this tautomer structurally rearranges. This tautomerization is acid catalyzed. Where would that acid come from? The reaction has sulfuric acid in it. So when the reaction produces this enol, that's what this intermediate is called. It's an alcohol bonded directly to an alkene, an enol. When the reaction forms the enol, the acid tautomerizes the enol into a ketone. So this reaction is regioselective. It is also Markovnikov. But it doesn't actually form your product directly. It forms a structural isomer that chemically interconverts. Keep moving along our circle, and we've got hydroboration, oxidation. Much like what we had before. I want you to notice that the only difference here is BH3 is now substituted for BH R2.
Is this supposed to be number 3 or is this number 4?
Well, if you'd be paying attention, instead of just blindly following what I put. Thank you for catching that. That should have been 3 and 4. The distinction here is that BH3 will clog up the reaction. BH3 actually reacts with 3 different alkynes, and it creates essentially a big molecule that gets really hard to react with. So we limit the number of hydrogens to just 1. So we'll represent this as BHR2. There are other ways to represent this. And I always forget them. Active gives you a version of BHR2 that I want to say it calls like 9 BBN or something. I actually can't remember, so maybe don't write that down, but if you run into something on active and you Google it and it says, oh, it's just a version of borane, then you're good. I don't need you to know what the structure is, because those R groups don't do anything. Their point is to do nothing. Gavin?
On the previous one, when you say regioselective, what does that mean?
Regioselective means the 2 groups added will go either to the more substituted or the less substituted carbon. And here, the H added less substituted, and the OH added more substituted. But in this regioselective version, it is the OH and H that swap, which is what gives rise to the aldehyde. This reaction is once again anti-Markovnikov. Do you see the distinction now, Gavin? One of them does hydration with OH on the more substituted. One of them does hydration with OH on the less substituted. That's why it's anti-Markovnikov.
So the state of anti or normal Markovnikov will determine the type of regioselectivity?
Yeah. Yeah, Markovnikov and anti-Markovnikov are regioselective terms. Good. Now, what if your alkyne doesn't have a more substituted or a less substituted carbon, and I wanted to do a hydration? Here, it wouldn't matter what type of hydration I form, or excuse me, what type of hydration I use, because there is no Markovnikov or anti-Markovnikov when the alkyne is internal. Both carbons are equally substituted. There's no hydrogens to worry about. So this one could be run with oxymercuration. This could also be formed by hydroboration oxidation. You guys see why it wouldn't matter which one you use? Because this internal alkyne doesn't have a Markovnikov or anti-Markovnikov. There's not a carbon more substituted and a carbon less substituted. So the difference is, do you have mercury sulfate in lab to use, or do you have a borane derivative to use? You wouldn't have to, you just work it out based on what you want to do. Yes?
So are these just the same, but one is anti-Markovnikov and one is Markovnikov, or are they totally different?
They're both hydration.
Okay.
So they're the same in that they add an equivalence of H2 and O,
Yeah.
but they are different in how they get there. Yeah.
But they're both tautomerized, right? Or is it?
They-
Like it's the same steps, they just have different.
Yeah, they're both tautomerized, but actually, remember here, the tautomerization was done by acidic hydrogen. Here, there's no acid.
Just happens.
How does it tautomerize? It actually uses base. Acid-catalyzed tautomerization, whereas here we do base-catalyzed tautomerization. Where would the base come from? Not the peroxide. Peroxide is not a base.
Or I guess sodium hydroxide.
Sodium hydroxide. This is basic aqueous hydrogen peroxide, and the reason we put in the base, part of the reason we put in the base, is to help with the tautomerization. So they're like equal and opposite.
Yeah.
They do the same thing, but they do it opposite.
The only reason they're called things that are so different is because of the.
Reagents, yep. All right, our last reaction on this side is oxidative cleavage. You'll remember that with alkenes, we had both reductive ozonolysis to form aldehydes and oxidative ozonolysis to form carboxylic acids. It turns out that with alkynes, there is no easy way to do reductive ozonolysis, so we'll only see oxidative ozonolysis. Now, I've pointed out that on this oxidation, you would create a one-carbon dicarboxylic acid. That one carbon on the end, let's map our carbons so that we can track that a little bit better. 1, 2, 3, 4. 3 and 4 gets split by this reaction. 1, 2, 3, 4. What we said with alkenes, was vinylic hydrogens get oxidized to OH. Well, in this case, that terminal carbon gets oxidized fully. Do you guys remember what that reagent is that it forms? H2CO3? Carbonic acid. And what happens when you form carbonic acid? It decomposes, makes water and carbon dioxide. So I want to show you, that's what happens with a terminal alkyne. What changes if you have an internal alkyne? Well, we still have that cleavage between the two carbons of the alkyne, but this time, since there's no terminal carbon, there's no carbonic acid. This time, it's 2 carboxylic acids. The regiochemistry matters. If it's a terminal alkyne, one of those carbons will get lost. It will disappear as bubbles in your reaction. If you're doing an internal alkyne, then you can cleave it and you get 2 carboxylic acids. Questions on these first 5?
That top one's a terminal alkyne?
Yes, you see why? The carbon chain ends at the alkyne. Yep.
So, but it's not always the case, though. It depends on the size of the alkyne that you're splitting. It's not always going to form carboxylic acid, though, right? Like if the chain was longer, right? Like
Where the carbon-carbon bond is cleaved, those carbons become carboxylic acids. If it's a terminal alkyne, one of them becomes a dicarboxylic acid. Does that make sense?
Yeah.
And it becomes that because it was already going to become a carboxylic acid from the cleavage, and the hydrogen that it's attached to also gets oxidized. Let's move to the back, the next page, where we see another 5 alkyne addition reactions. We'll keep going. We're going to start in the same place. We're going to start in the top left and move around. Can I ask you to point out what is the difference between the alkyne used in the example here versus the alkyne used on the last page?
terminal versus.
So I did this intentionally. The first 5 that I gave you were shown on a terminal carbon because there is regiochemistry relevant. The next 5 are shown here because regiochemistry is less relevant, but stereochemistry is relevant.
Does that mean all of these ones are antimicrobial?
Actually, none of these. No, you're talking about the first set, the first 5 we did?
Yeah. No, the second set.
The second set, they don't apply to Markovnikov at all.
It's not relevant because
They're either not adding hydrogens or they're adding hydrogen in both positions. And Markovnikov's rule limited itself to saying hydrogen adds only to the carbon with more hydrogens. So these are actually neither Markovnikov nor anti-Markovnikov. First, halogenation, 1 equivalence. You know this mechanism. You showed it on the unit test. We did it in class last week. It's the same thing that happened with the alkene. The alkyne attacks bromine, bromine attacks back and kicks off this bromide. This time, our bromonium ring has a pi bond in it still. But it's still a backside attack. It's still anti-addition. The only difference is that you've got 2 equivalences of pi bonds to go through.
Do they add syn or anti to each other?
What do you think?
Anti, right?
Is it a cis alkene or a trans alkene? Trans alkene. The halogens are trans to each other, they're anti. So it's still an anti-addition mechanism. If we add two equivalences, or if we run this in excess, after the first equivalence has reacted, a second equivalence reacts. I just realized I'm not doing this with X this time, even though your sheet says X. So I've just picked a halogen to show this with. There's a lot of bromines going on. But these two-step mechanisms, they're not that challenging. It's repetitive. It's the same thing over and over and over.
So did you just start with the product of the first one?
If you're okay with that, because the mechanism for two equivalences includes the mechanism for one equivalence and then just follows it in that second equivalence. You'll notice that we are not doing haloether or halohydrin mechanisms like we did with the alkenes. That's because haloether and halohydrin don't work in quite the same way with the alkynes. Questions about this? Halogenation, two equivalences. We can say the product gives us a vicinal tetrahalide. Across two carbons, we've added four halogens. What's the chirality of that product? Is it achiral, chiral, or meso? Achiral. Neither of those carbons are chiral because they have two identical groups on them, two halogens. All right, let's keep moving counterclockwise. Do you know there's research coming out that shows humans instinctively like to move counterclockwise? If you guys go down and look at Liberty Park, do you know what direction people lap the park? Counterclockwise. Do you know what direction track and field runners run? Counterclockwise. NASCAR? Counterclockwise. Kentucky Derby? Counterclockwise. Name a single event that we do in a circle that doesn't run counterclockwise.
Steering gear and seat.
I actually do it both ways, so I guess that is up to you. As we move instinctively counterclockwise, we're going to look at partial hydrogenation. There are two partial hydrogenation reactions. The first is hydrogenation with Lindlar's catalyst. It's not really, these aren't events, though. That's not like an activity that humans participate in. Lindlar's, oh, I messed up. No, I messed up. The reagent there should not, the reagents are swapped.
Which, the NaNH3?
The NaNH3 and H2 with Lindlar's catalyst are in the wrong spots. So I'm gonna draw what the correction should look like. Right now we're pointing down, and that should be H2 with Lindlar's catalyst to form the cis alkene.
Not the sodium and the ammonia.
Right.
Okay, so
The cis alkene is formed by this reaction. I'm sorry. And the one that goes up to the right to the trans alkene, that should be sodium and ammonia. Sorry, I'm sorry. Ah, man. Such a silly little mistake. lucky you. If you've got it in paper, you're going to want to scribble it out. Lindlar's catalyst is not a reagent. I'm going to ask you to know. And that doesn't happen very often, that I give you a reagent and don't care for you to really know what it is. But Lindlar's catalyst is a hodgepodge of things. It's not one thing. In fact, what his catalyst is, Lindlar's catalyst is a poison. It prevents hydrogenation of the alkene. Is hydrogenation with Lindlar's catalyst syn addition or anti-addition to the alkyne? Right. Once you've corrected the reaction diagram, this is a syn addition reaction. It's because the palladium creates a surface that the hydrogen disassociates onto, and then the alkyne or the alkene, they actually approach it from one side, and they form their bonds from the same side. It's because the alkyne and the alkene, they sit on the palladium surface and pick up hydrogens on one of their faces, syn addition. We saw that hydrogenation was syn addition for our alkenes last week. Nothing different here, except that we don't give both equivalences. The catalyst poisons the alkene from reacting. The other partial hydrogenation is metal in ammonia reduction. And I want you to tell me what you think most people will confuse NaNH3 with. When you as a student see NaNH3, what might you accidentally think of? Another reagent we've used. What base? NaNH2. Sodium in ammonia is not the same as sodium amide. What is the charge on sodium in sodium amide? Yeah, because it's part of a chemical, it's a cation. So this is sodium ion and amide ion. What is the charge in sodium in ammonia? What is the charge of sodium? That's neutral. It's not a part of a chemical formula. It's not bonded to anything. We're just saying introduce elemental sodium. Not to mention ammonia, NH3, is neutral, unlike amide, NH2 minus. But it is so easy to see those as looking too similar and confusing what they do. Okay, what type of addition is this? Good. This gives us a transalkene, which means it's anti-addition. And I want to come back. I'm going to give you guys the mechanism for this. But I want to show the last reaction for our alkynes before I give that mechanism. The last one is complete hydrogenation. Where we introduce the same reagent as with alkenes, hydrogen with the palladium carbon catalyst. Those of you guys in my lab yesterday, you literally did this. Well, not with the alkyne, but with the alkene. You took palladium with charcoal. You mixed it in, bubbled in some hydrogen. That's what you guys did yesterday. When you have an alkyne and you run it through complete hydrogenation, it has to do hydrogenation in steps. First, one equivalence of H2 is added, and syn addition alkene is formed. But we know that alkenes go through hydrogenation because that was the point of your lab this week. So this alkene also goes through hydrogenation. Hydrogenation of the alkyne is a two equivalence hydrogenation. First the alkene, then the alkene gets hydrogenated. This is the importance of Lindlar's catalyst. Without Lindlar's catalyst, alkenes are reactive to hydrogenation. We know that. With Lindlar's catalyst, it poisons the alkene. It prevents the alkene from reacting further, which is useful. If you really want to have the alkene and you don't want to fully reduce to an alkane, Lindlar's catalyst is useful. Okay, I want to give you the mechanism for this metal in ammonia because it's our first radical mechanism. It also does a really good job explaining why the alkene is trans. Saray.
For complete hydrogenation, would we just use hydrogen and the palladium catalyst?
Yep. Yeah, actually, the hydrogen is always assumed to be in excess. The other thing is sodium and ammonia, we need two equivalences of both. We don't say it. So this is actually where organic chemistry often just forgets about balancing. It does require two equivalences of sodium and two equivalences of ammonia, and we don't really we don't say that. We do say it with halogenation and hydrohalogenation. We say whether we're adding one equivalence or two. But for these reactions, it's always assumed to be in excess.
Is that because you can't do anything with just one equivalence? Like it has to be multiple, so you wouldn't specify?
It's more that it's hard to get hydrogen to be the limiting reagent. It's hard to provide a limiting amount of hydrogen gas. It's easy for it to be in excess. It's very easy for it to be in excess.
That makes sense.
All right, I want to show you this mechanism. And to show you guys that these partial hydrogenations, they don't have to be done on internal alkynes. But you see the stereochemistry implication. Lindlar's catalyst gives a cis alkene. Metal in ammonia gives a trans alkene. But if it's not an internal alkyne, if it's a terminal alkyne, it doesn't matter whether you use sodium in ammonia or Lindlar's catalyst because a terminal alkyne doesn't have stereochemistry when it becomes an alkene. So I'm going to demonstrate it on this one because it doesn't really matter. No, actually, well, anyways, yeah, maybe I will. But I wanted to show you stereochemistry only applies when it's an internal one. All right, the first step of this mechanism is, no, you know what, I don't want to waste the time with naming the steps. This isn't a mechanism you have to reproduce. So this would be a mechanism to watch if you want the learning experience. And for that reason, I am going to go back to the other one. This mechanism requires two equivalences of sodium and ammonia, so I'm going to show them both. Sodium, elemental sodium, is a radical species. It has one valence electron, and it's a very strong reducing agent. So what happens is sodium gives away its one electron. Do you remember how we use arrows to show one electron? Fish hook rather than a double hook. Just one line to show one electron moving. There are two possible arrangements here. This new radical lone pair species can either be cis or it can be trans. We know from what we've already been shown that it's going to be trans. So can we rationalize why the intermediate prefers to form trans rather than cis? What would you say?
Because of the electron cloud shells that are repulsing.
Repulsive electron forces. Non-bonding electrons repel more than bonding electrons do. Non-bonding electrons have the greatest repulsion. And here, I've got my non-bonding electrons on the same side of the molecule. So I've got my non-bonding electrons as close together as possible, meaning they are as repulsive as possible. High repulsion.
Can you call this strain or just?
Absolutely, we can call it strain. I think most of our strains have been repulsion. Torsional strain during eclipsed conformation is just the result of those electron pairs repelling each other. That is the strain. So it doesn't form the top configuration, it forms the configuration on the bottom. That gives us sodium plus our second equivalence. And now ammonia serves as an acid. So we protonate our new alkene. We still have a radical, and we generate a byproduct. And look what that byproduct is. Sodium amide. So as if it didn't need to get any more confusing, sodium and ammonia is not sodium amide, but sodium and ammonia produces sodium amide. Then our second equivalence of sodium acts as a radical to the radical, creating a lone pair species. And that lone pair behaves just like it did last time. Takes a hydrogen from ammonia. Generates our new trans alkene and a second equivalence of sodium amide. Why does sodium and ammonia make a trans alkene? Because of electron repulsion in that radical anion intermediate. Why does Lindlar's catalyst make a cis alkene? Because of the syn addition from the palladium surface and the poison from the catalyst. Now you know everything you need to know about alkynes, except one thing. So radicals have predictable stability, just like carbocations. And we're going to talk a little bit about radicals before we wrap up this unit. Can you name that molecule? Methyl cyclohexane. If I could take one hydrogen off of this molecule and leave in its wake a positive charge, where would be the most stable position to put that positive charge? At number one, the carbon bonded to the methyl. Is there any other regio descriptors we could use?
Most substituted.
At the most substituted carbon, in this case, the tertiary carbon. So this is the most stable carbocation position. And what I want you to know is that radical stability trends with carbocations. So where's the most stable place to take a hydrogen and leave a radical? At the most substituted carbon. Are you guys okay if we abbreviate carbon radical like this? Well, I'm not, because I don't like the way it looks. Carbocation, I've been abbreviating as C+. Carbon radical, carbon C dot. So our most stable carbocation would have been this tertiary carbocation. Our most stable carbon radical is this tertiary carbon radical. This does not mean that everything becomes more stable on a more substituted carbon, because remember, negative charges are the opposite of positive charges. So negative charges have opposite stability of a positive charge. A negative charge is more stable on the less substituted carbon, where there's less electron repulsion. But a radical is not a negative charge. In fact, it's still electron deficient. So it is looking to be swarmed by electron density to make it less reactive. What about on our next structure? First, can you name it? You gave a locant for the alkene, but you didn't give a locant for the methyl. What's higher priority? The methyl is not higher priority. What's the highest priority functional group? The alkene is the highest priority functional group. So we don't need to number where the alkene is. But we do have to say the methyl groups.
Would it be two?
One methyl.
Oh, because we can go the other way.
But you do have to put a number for the methyl.
We do have to give a number for the methyl. And we don't have to. We could call it 1-methyl, 1-cyclohexene. We could call it 1-methyl cyclohex-1-ene. We can call it 1-methyl cyclohexene. But we can't call it methyl cyclohexene. We have to give a locant for the methyl group, because we can only assume where the highest priority group is. And we won't name it 2-methyl, because that would be a higher locant set than 1-methyl. Where's the most stable place for a carbocation to go? If I could take a hydrogen off of here. So here,
Yeah, if you read the
No, the next one.
there's no hydrogen here. Would you agree?
Oh, yeah, you're right.
I can't put a positive charge there.
Further down to the left, on that tertiary.
No. Because it's an sp2 carbon. If I take away that hydrogen, it becomes an sp hybridized carbon. sp hybridized carbons have linear geometry, and I'm still trying to have this be part of that 6-membered ring. Look fun? Looks uncomfy. So it's actually not great to put it on a vinylic position. No vinylic carbocation. Don't forget, we did see something like that when I gave the HX addition mechanism for the alkyne. You remember we saw something just like that. It can be an intermediate. It's not a good intermediate, especially in a ring. So you're looking for the most substituted position, but remember, carbocation stability increases with resonance. Starts over again, even at low degree of substitution, and it increases with resonance. So I want to put the carbocation allylic. I want it to be adjacent to the alkene so that it can be conjugated to the alkene, completely in resonance, an uninterrupted series of p orbitals. I'm looking at allylic positions. How many allylic positions are there? 2? Actually, let me ask you this. What is the degree of substitution of the alkene? Mono, di, tri, or tetra substituted? It's a tri-substituted alkene. It has 3 carbon groups coming off of the alkene. So I'll ask again, how many allylic positions? If it's tri-substituted, if there's 3 carbon groups coming off the alkene, there should be 3 allylic positions. So allylic, allylic, allylic. All of those would be good places for a carbocation. Guess what? They'd all be good places for a carbon radical as well.
Would the secondary carbons be better than the primary carbons?
Yes. Least preferred is the least substituted. Maybe least preferred is the wrong way of presenting it.
The most preferred is the most substituted.
Least stable. Yeah, and the other two are equally substituted. Would you agree? So the other two could be seen as equal, but there is a distinction between the other two.
So the least substituted is the least stable.
Yes. Yes. I want you guys to see 1,3 allylic resonance. Remember early in the semester when we introduced resonance, we said that there's two types of resonance. There's a 2-atom system. That's where an electron-deficient atom is next to an electron-rich atom, and the electron-rich atom shares with it. An electron, or most resonance forms are 3-atom systems. 2 atoms in a pi bond, and a 3rd atom with a charge and maybe a lone pair. And those 3 atoms are in resonance. So allylic and the 2 carbons of the alkene, that's my 1,3 allylic system. I've got those positions. The pi bond always stays at carbon 2, and then that charge moves from 1 to 3. So if we take this allylic position on the bottom left, let's make it a carbocation, and then let's show the resonance form that it creates. At the same time, we'll take the secondary position on the right, and we'll show the resonance form that it makes. If we say that our first resonance form has the charge at 1 and the pi bond at 2 and 3, what I want you to use this 1,3 allylic resonance for is to say the charge was on 1. Now the charge will be on 3. The charge is split between 1 and 3. This resonance form on the top, electrons flow from the pi bond to the carbocation, to the deficiency, and it leaves in its wake a tertiary carbocation. The other position, if we say that position 1 has the positive charge, then the other allylic carbocation is actually symmetric with its resonance form. They're identical to each other. So they both form secondary carbocations, secondary allylic carbocations, but one of them is in resonance with a tertiary carbocation. The other is in resonance with a secondary carbocation. Which resonance form exists? Right. All of those were right. Both exist, none of them exist. The major contributor is what the molecule looks like the most. The resonance hybrid is kind of what the molecule looks like. So it's to say, I don't have either of these, but actually I have both of them. I don't have either of these, but actually I have both of them. So forming the allylic position on the right, it actually just splits the resonance form equally between these two. But forming the allylic carbocation on the left, it gives you a most stable resonance form. Exactly. This form is the most stable out of any of the options that could have formed. So what I wanted to remind you about here was allylic resonance. What this looks like now in the context of the radical is that, once again, we will form the most substituted and most stable carbon radical, and that radical will be found to be in resonance. What changes is the electron arrow pushing. Because now I can only use fishhook arrows. I'm not showing lone pairs moving anymore. I'm not showing pairs of electrons moving. I'm showing radicals moving. And I don't know about you, but I find those arrows are harder to read. Yeah, I said that, and then Evelyn's like squinting as hard as she can. So let's see what we can do with radicals, shall we? First, I want to show you guys radical halogenation of alkanes. If you're paying attention, this is the first reaction where alkane is the starting material. We've shown alkenes, we've shown alkyl halides, we've shown alkynes as starting materials. This is our first time saying if I have no functionality, but I have an alkane, now I can put functionality onto it. Earlier, Michael was asking, what if I want to make an alkyne, but I can't make an alkyne? What if I have an alkane? Can't make an alkyne because there's no leaving groups. If you have an alkane, you can halogenate it. And now you can do elimination. Some things about this reaction. You won't see us use chlorine. Earlier I was saying if I put X2, you need to be specific about which X2 you're actually using. No more, because I'm not putting X2 on this reaction. I'm only putting Br2. Chlorine is too reactive, can't be controlled.
Is this the top middle one?
Yes, it is, direct, straight up. There's no regio control with chlorine, so we don't use it. But bromine is just reactive enough that it gives us regio control. What do you think I'm trying to get at there by saying it gives us regio control? Where will it be placed?
Like on most substituted.
It will go to the most substituted carbon. Exactly.
So it's like Markov-Nikov, but radicals?
It's like Markov-Nikov, but radicals. And that's exactly the point, because Markov-Nikov identified, without realizing it, that his carbocation was going to the most stable place. It wasn't about where hydrogen was going, it was about where the carbocation was going. It's the same thing here. The most stable radical will form. The most stable intermediate will form. How about radical halogenation of alkenes? We'll see this change now. If there's only alkane, put it on the most stable position, the most substituted carbon. But if there's already an alkene present, we'll always form an allylic halide. What do I mean by allylic halide? I mean the radical will be in an allylic position, and the halide will add there. But did I form just one allylic halide? Because when you look at that reaction, it looks like there's two different allylic halides that formed. Those are 1,3 allylic isomers. They come from the 1,3 resonance forms. Both radicals react. Both radicals exist. Good question. I'm going to pass this to the class. Someone define allylic. It's a good term. It's very helpful to know. Adjacent to an alkene. So, Gavin, here's the alkene. Here's a position allylic.
So carbon adjacent to alkyne.
Good. You guys will notice that in the product, you're given a halide adjacent to the alkene, allylic halide. Okay, there is one thing to answer about these two reactions, and that is, what is HV? It's actually H nu, the Greek letter nu, which subs in for frequency, and H is Planck's constant. When you multiply Planck's constant times nu, you get the speed of light. No, you get the energy of a photon. So we use H nu as an abbreviation for light. What drives the radical reaction is ultraviolet light. Ultraviolet light creates the radicals. You're what?
I was mentioning, they talk about radicals a lot in sunscreen ads and stuff like that.
Oh, interesting. Yeah, because the UV light can split things into radicals. All right, as we keep moving along, we've got the last three reactions are essentially the same thing. It's anti-Markovnikov HX addition. You could also call this HX addition in peroxides. It's the bottom right, the bottom left, and the top left. It's anti-Markovnikov HX addition to alkenes and alkynes alike. So as a reminder, we said that an alkene goes through HX addition, forms a carbocation. I'm skipping the carbocation rearrangement. We've talked about it enough. The carbocation forms a most stable spot, and then the halide adds. What's happening now is the peroxides is changing the chemistry. The peroxides are creating oxygen radicals, and the oxygen radicals create halogen radicals, and the halogen radicals create carbon radicals, and it's the carbon radical that finally takes a hydrogen. Once again, where does the radical form? The radical forms on the most stable carbon, the most substituted carbon. So why is it anti-Markovnikov if charge is still being stabilized? Because instead of adding the hydrogen first, we're adding the halogen first. What's the password? I know. If you add the hydrogen first, that's acid-base chemistry. Most stable carbocation, halide goes to the more substituted position. If you add the halide first, most substituted radical, anti-Markovnikov. It's because of the intermediates that we get the difference in regiochemistry. Why did I not introduce this reaction last week? We went through 12. Would it really have been that hard to just say, by the way, there's another HX that just does anti-Markovnikov? It would not have been that hard. but a lot of textbooks will save it and group it with all this radical chemistry. Listen, I could take the time to draw these mechanisms, but I will not be testing you on these mechanisms. So what I could do instead, we've got 15 minutes remaining, and the only thing left that I want you to do is apply these reaction diagrams to this roadmap, the two roadmaps. I just want you to practice providing reagents and drawing structures. While you do that, I will draw the mechanisms for these radical halogenations, because I think they're interesting. And you're welcome to take a picture of them or take down the notes or ask questions about them. But you won't be tested on them. So I'd rather you spend 15 minutes on this than just watching me do fun stuff. Please feel free to work in groups. If you feel like this comes naturally to you, take it slow and find someone that needs help so that you can work through it more slowly and really solidify it. When you teach someone else, it solidifies it so much better for you. So be selfish. Help someone else today. Okay, the rest of the time is yours, and I'm here to answer questions. That's mercury. I think quite famously, mercury.
I think that top one is on the one with the more specific.
I don't like
It's like, I mean, I have this.
the rings. But yes, they're never. No, the rings just fucking chill out.
Next
The
one.
rings just chill.
The BR2 would that be the extra box?
It's an Alkynes.
Oh,
It's an Alkynes.
yeah, so I think it should form a general tabulate, right?
I can
Right,
see.
oh, it's a, oh, it's a, oh, it's that one, yeah. So what we're gonna do is
Activation,
the top one.
halogenation, one of them.
So oxymercury. I know what it's called. Got it. Wait, they put it on.
Oh.
What happens? Oh, was it mercury? Oh, mercury sulfate.
How would you know the difference between the 1 and 2 equivalents? Would it have like 2 separate PRs? Or would it show 2 steps?
Well, there's two different reactions that have one or two equivalents, HX and X2.
Yeah.
Which one are you talking about?
Well,
Either one.
Either one, because it'd be BR and a BR, or a BR2 and a BR2. Or whatever halogen.
Well, yeah, HBr, HBr,
Yeah.
or BR2, BR2.
Okay, yeah.
If it's one equivalence of HBr, you're left with a vinylic halide. If it's one equivalence of BR2, you're left with a trans divinylic halide. Because HX will add one hydrogen and just one halide, but X2 will add two halides.
I'm just asking, like, on the reaction, would it show multiple BR2s if it was?
Oh, it would say just like it did in here, it would say one equivalence or two equivalents.
It would have to say that.
Yep. Unless the question itself said something like, show the one equivalence addition, and then the reagent might not have to say it. But otherwise, that is something that would have to be clarified. Good question. Yes, I'm listening.
Okay, so for the BR2H2O,
Yes.
in the example, it shows like where the halogen will go and then where the alcohol will go. Do they always end up there? Is there like different because like I have OH here BR because like that's how it is on there. Could these
Regio selective is what we say.
Okay.
And what is the regio selectivity? Halogen on the less substituted, oxygen on the more substituted.
So it's not necessarily about the left and the right.
It's never about left and right. Do you know what? That's similar to what Michael asked yesterday, I think. Why does it go to the left and not the right? Left is arbitrary. Spin around and we're looking at the right. No, it's about more substituted or less substituted.
Okay.
Yep.
So this is right
It is.
because that's more substituted.
Perfect. Think about the halonium ring that forms. Where will water attack? Will it attack at the smaller partial positive, less substituted, or at the bigger partial positive, more substituted?
I'm confused.
I think you lost a carbon.
Well, I was gonna do that.
That's great. That's exactly right.
Oh, really?
What are you confused about?
I don't know.
Okay.
And then I have but we're not doing stereochemistry here, are we?
No, you're right. I didn't pay attention to the stereochemistry. If you wanted to, you could say there's one chiral center,
Right.
and it could form wedged or dashed, so I get a racemic mixture.
Because I could have my wedged chlorine and my dashed hydrogen.
Yeah, but keep in mind that's not the hydrogen that added.
No.
Right. But really, the hydrogen adding didn't make a chiral carbon.
Are you doing this without looking at the chart? Huh? Are you doing that without looking at all this? Yeah.
That's okay. Keep practicing.
Trying to.
Use those charts until you feel like you don't need them.
Making it
With the answers. Do you like my cheat sheet?
Not really. That's wild.
I've always done them this way.
I say that, but if it works for you, that's what's important.
You know, I did in Chem 2, we had practice exams, and I wrote the whole practice exam with the answers
Wow.
from the practice exam, and then how to do it.
You like wrote out the word problems?
Yeah.
Oh, so then you got into the exam with a cheat sheet
Yeah.
and you had all of the questions.
Literally.
Okay. That's not a bad way to do OCHEM either.
It took me like 6 hours
Put
to make.
examples. Put examples. Do you know you're going to have a mechanism on your final? 2. Have an example of your mechanisms.
Have every example.
If you want it, yeah. Or what I would say is, if you're going to have an example of HX addition and acid catalyzed addition, just do acid catalyzed addition because it's just HX addition, but a little bit harder. If you can do acid catalyzed hydration, you can do HX addition. If you can do halo ether and halo hydrogen addition, you can do halogenation. So put the harder example, if anything, or put every example.
I got my chair flips.
There's a lot of colors though, so you know what the colors mean.
Yeah, it's like schizo.
Actually,
I'm the same way. If it's not color coordinated, I'm
No.
just not.
And I use
is it
highlight-
not color coordinated?
It is, and I use
Oh, right,
highlighting
right.
to like highlight the sections to like separate them.
Yeah. There's definitely like
Something.
there's thought put into it, but if it wasn't your thoughts put into it, it's hard to actually interpret. It's a lot going on.
Yeah,
It's very bright.
Thank you.
Any questions I can answer?
Well, I think this one right here on the right is HXR, double RO.
That is right.
Right, yeah.
It's a lowercase h for phenyl.
With what would be considered, like the product like COH2, would it be the,
Oh,
it'd be basically the chain of reaction though, but would it be like the O3H2O2 or no?
Did you notice that a carbon was lost?
I did, yes, saw like this whole thing was lost, so then.
Well, kind of, but actually the first carbon off of the ring is still there. The second carbon off of the ring is gone, which is different than here,
Right,
where both of the carbons remain.
right.
So this is a
So
cleavage reaction. We are cleaving a carbon off. Is this a cleavage reaction?
it is not.
Oh, actually, it is. Its name is oxidative cleavage
No.
because it cleaves that carbon-carbon bond. I think maybe what you're stuck on is the abbreviation CO2H
Probably.
is COOH.
There we go, yes.
CO double bond OH.
COH, okay. There.
So I'm glad you caught that because I want you to know I want you to know both bond line structure and its condensed structure. Good. Yes.
So this question.
Oh. Yeah.
Okay, so it's hydrogen with this.
Yeah.
Whatever. How do we know if it's 1 or 2 when we're going
Oh.
to draw it?
Well, here it doesn't matter.
Okay.
Why?
Because it doesn't specify.
What starting material? What is the functional group that we have in the starting material?
Like the alkene? Is that
Yep.
what it's saying? Okay.
And the 1 and 2 applied to what? To what starting material?
An alkyne. Oh.
Alkenes can only do one addition.
Right. Okay.
An alkyne we have to distinguish. You know, that's what Andrew was asking earlier. Were you talking about the reaction with the alkene that just says HCl? And you were asking, what do I do if it doesn't say 1 or 2 equivalences? It's not an alkyne. Only alkynes
only have 1 or 2.
can do both equivalences. Alkenes can only do 1 equivalence. So if I said HCl 1 equivalence, the same thing would happen if I had extra equivalences. Those extra equivalences just wouldn't react.
Okay.
Great questions. I'm glad you guys are picking up on that. Being able to make that distinction is important. So you guys are catching on that you need both your alkene addition reactions and your alkylation or your alkyne reactions. How you doing? The alkenes
No, the alkyne.
to practice them. Yeah.
So, in this example, it goes to the other substituted carbon, right?
It rearranges.
But here, it's a ring.
Okay.
So, would the chlorine go into the ring, but then we lose a carbon? So
The ring is very inert. So the aromatic ring,
you don't really.
yeah, just no, you won't mess with it. So remember that this is a carbocation mechanism. HX addition forms a carbocation intermediate. That carbocation always goes to the most stable carbon.
Right, most substituted.
And if the most substituted carbon is able to rearrange, that's what this example is showing you, is that rearrangements are possible. Where's the most substituted carbon for the carbocation?
Right here.
Well, that's actually not part of the alkene.
Okay.
Do you agree? Like
Well, it's coming off.
it's got to be one of the two carbons of the alkene. Of the two carbons of the alkene,
Well, they're equal. Wait.
which one is more substituted?
Oh, here.
Sure.
Here.
Of the alkene, of the two carbons of the alkene, which is more substituted?
Well, they're equal.
No.
I'm confused with.
This carbon is bonded to no other carbons, but this carbon of the alkene is bonded to another carbon.
Okay.
This is a more substituted carbon in the alkene. This is a less substituted carbon in the alkene.
Okay.
Where will the carbocation go?
To this one.
This carbon is not part of the alkene.
Okay, I'm so confused. Okay, we'll go here.
Yes, the
Yes.
carbocation
Yes.
goes to the most stable position. When it goes there, we have to consider, can it rearrange?
Right.
And the answer for this example was
Yes.
yes, it can
So
rearrange.
this one can't. So this one.
Well, let's start all the way over again, though.
Okay.
Which carbon is more substituted?
This one.
So where will the carbocation go?
Right there.
Good. Can it rearrange?
No.
No, there's no hydrogen here because that's a carbon of the aromatic ring. There's no hydrogen for it to shift. Perfect. So I think the answer.
I think I get confused with the substituted because it's like how many carbons come off, and then I want to go. Well, I mean, no. So the carbon goes off too instead of
Yeah. Oh, I see.
that side.
Yeah. hmm The other thing I think you realized here is the carbocation has to start on one of the two carbons of the alkene. Then it has the chance to rearrange only if it's able to rearrange or stable. Alkynes never rearrange. You might have noticed in our alkyne addition mechanisms, we had that. Well, they weren't good examples for rearrangements either, but they don't.
Okay,
They don't rearrange. Yeah.
that's good to know.
Oh, that's time. You guys are welcome to stick around if you want to keep working on it. This is lovely to see. Tomorrow, I have a new worksheet. If you'd like the worksheet for tomorrow today, I'll hand it out. Otherwise, I'll hand this out tomorrow. And we are in our last set of, this is the last packet I have for the class. So if we don't finish this, you can finish it with Natalie next week. You can watch lecture recordings that kind of touch on this, but this is a newer packet. So if you want one of these on your way out, let me know. Otherwise, I'll see you tomorrow. And if I don't see you tomorrow, good luck with the rest of the class. Good luck on your finals. I know that's